Hello, my name is Tristram Dacayan. I go to Kean University in Union, New Jersey, and for the RISC program, I had the opportunity to work with Dr. Zaki Hamal to research video regression for automated pain assessment using the video masked autoencoder architecture. Pain is a sensation that every person has felt in their life, which can derive from several different sources and can be affected by varying internal and external factors. Therefore, medical professionals require conducting proper pain assessments in order to properly treat a wide range of disorders and injuries. To do so, they generally employ the use of either the Visual Analog Scale, VAS, or the Numerical Rating System, NRS, an example of which can be seen on the figure to the left. Although these assessment metrics are considered the medical standard, there is very little standardization to these metrics. The main concern of these metrics is the subjectivity of the reports, as pain tolerance varies from patient to patient. It also is very difficult to record data from non-adult and non-communicating patients. Therefore, we look to nonverbal assessment to look for changes in the person's appearance and reaction to pain. To help, the Facial Action Encoding System, or FACS, was introduced to identify changes on the person's face via common landmarks called action units, or AUs. For this project, our main contributions are as follows. We first proposed the use of the video masked autoencoder, otherwise known as VideoMai, transformer architecture to perform video-based analysis to predict the pain scores by appending a regression layer to the output of the decoder module. To train our model, we then developed a secure training pipeline to read encrypted video data from the cloud and utilized the two-level k-fold cross-validation method based on Arakat et al. To evenly train the model on all parts of our dataset. Some of the more recent automatic pain assessment models utilize a mixture of both classical and modern machine learning algorithms. Deep Facelift, considered state-of-the-art for APA models, employs the use of a pipeline that would first extract faces from a frame using the landmarks on a participant's face, sending them through a neural net, and then passing the output through a Gaussian regression model to estimate the continuous VAS scores. Arakat et al. Did something similar, instead opting to use a CNN plus RNN-based architecture, having the CNN learn the spatial relations, while using the RNN to determine the dynamic changes. The most recent iteration has been done by Shepa et al. Using gram matrices to analyze the trajectories of the facial landmarks, and then using an SVR to analyze and predict the output score. For our training dataset, we use the UNBC McMaster Shoulder Pain Expression Archive, which is a common benchmark for most automated pain assessment-related research. This dataset includes a total of 200 video sequences ranging from 10 to 15 seconds long, taken from a total of 25 different patients. This dataset includes many different recorded metrics. However, for this project, we mainly focus on VAS. In the paper by Arizat et al., they outline the idea to extract faces from the video to remove noisy inputs from the background. By focusing solely on the face, the model will be able to focus just on the changes to the face rather than the changes to the patient's surroundings. The method for generating these registered faces can be seen in Figure 1. So why did we choose to use a video masked autoencoder over another transformer architecture? First off, here's a little background to the model that we chose. The video masked autoencoder, or VideoMai, is a continuation of the image masked autoencoder, rightly named ImageMai, which combines the use of a masked autoencoder and the transformer architecture. Essentially, ImageMai randomly masks parts of an image to force the network to understand the relation between certain sections instead of simply copying the input image. ImageMai then leverages the use of the transformer architecture's attention mechanism to increase the training speed and accuracy. To ensure training goes on, the network first learns the unmasked patches through the encoder, and then attempts to reconstruct the image using the remaining unmasked features and learned masked tokens in the decoder module. This idea is mimicked in the VideoMai architecture. However, because there is a naturally added dimensionality for the videos, VideoMai downsamples the video to reduce temporal redundancy and introduces a high masking rate to compensate for the increased number of inputs. Therefore, VideoMai is then able to introduce a method to train a video vision transformer, or a VVIT, without using a pre-trained backbone, while still outputting better performance with a lower resource cost than other VVIT and CNN plus VVIT architectures. Here's a diagram for our proposed training pipeline. For the input, we used a modified version of the UNBC dataset outlined in a previous slide. This dataset only consists of registered faces of the participants. In compliance with HIPAA regulations, This dataset is securely stored on the cloud in an encrypted non-spatial temporal format. To start, these files are first read from the cloud and sent through the dataset compiler module. This module decrypts the videos and reconstructs them into readable spatial temporal representations. After reconstruction, the patient's ID and label ID are taken into account, and the videos are pre-processed to match the model's pre-trained image processor via cropping, flipping, and clipping. This dataset is then passed through a two-level k-fold dataset splitter. Because of the limited amount of data that we have access to, we want to decrease the possibility of bias during training. Therefore, the dataset is then split into 5 equal non-overlapping folds, of which one is set aside as the testing dataset. The remaining folds are then resplit into 5 folds once more to form the training and validation sets. This method iteratively chooses a new fold to become the training, validation, and testing set respectively. The fold that is chosen to be either the validation or testing set is switched after every iteration, ensuring that every fold is used either for one of those 3 purposes. Once the current split has been determined, the dataset is then sent into the VideoMai model, which applies a custom tube mask to the video and sends it through the encoder-decoder pair. The output of the encoder-decoder pair is then sent through a regression layer to return a continuous value prediction when evaluated and used for inference. This model is then sent to an inference/testing module along with the testing dataset to test its performance. Here are the experimental training results of our model compared to the other pain assessment models previously mentioned. This includes a state-of-the-art model at the top. At the moment, training for our proposed model is still ongoing, so the evaluation may not be entirely representative. However, our proposed model shows promising results, showing potentially competitive error evaluation scores compared to the other models with the same dataset, validation method, and measured pain metric. To conclude this presentation, I would like to reiterate some of the contributions that were made in this project. We firstly proposed a pipeline to securely read video data from a modified version of the UNBC McMaster Shoulder Pain Expression Archive, and using k-fold cross-validation, trained the VideoMai model on all facets of the dataset to compensate for the low number of video samples. Through preliminary training, we were able to infer that our model shows increasing promise as we continue optimizing the hyperparameters and adjusting the masking ratio of the model. While training is still ongoing and the preliminary results are unrepresentative of the model's true performance, the model's current performance alludes to the model being very data efficient. For future work, we intend to continue our ongoing training to generate more representative training results. We would also like to compare VideoMai to other state-of-the-art video vision transformers, as well as perform evaluation studies to determine the best hyperparameters for our model. That concludes the presentation, and I hope you have a good day.